I am ready. So thank you for the organizers for letting me give this opportunity to talk about our very new research results. I will talk about the periodic motion in the chaotic phase of an unstepped furin catalyzed Belousov Zhabotinsky reaction. Before I go into the details, I would like first to give a slight overview about what is actually chaos. And here, if we go to, according to Richard Kautz, it is the science of predictable random motion. But are there different types of chaos? So first of all, there are at least two different aspects of chaos. We have the statistical one, which is connected to the randomness, and there is also the deterministic aspect, which is normally connected to the sensitivity to the initial conditions. We look here at a very simple mathematical model. We have seen it today already. It's the logistic map. And here we have a parameter, this lambda, which for certain values goes to the chaotic regime. And we have here plotted from an application for lambda is equal to 4, the evolution of the system. And we can see here, if we look down, it is actually done for 3 different initial conditions, which are very close to each other. And if we look in detail on the evolution, we see that in the beginning we have the same more or less evolution, but after some time they diverge. And this is what is normally called the sensitivity to initial conditions, and which is normally connected to the what is called the deterministic chaos. But at the same time, in the same system, if we look split the how to say the be seen as a random series. So we have here both aspects of chaos in the same system. Now let's see if there are different types of chaos in different, let's say natural systems. So to my knowledge, the first time when there was a natural system talked about chaos is when there was the transition to turbulence. It was a very important paper by Sweeney and Golub in 1978, where they, among other systems, were looking at the rho binary instability. And they found out this is actually the evolution of convection cells, which is here shown in a numerical simulation. And it was shown there that there is a transition to a turbulent state, which can be seen as a transition to chaos. And it can be characterized, which is one way of characterize this transition, is by looking at the Fourier spectra. And if we look, for example, here in this line, the velocity component of the field, the velocity field, we can see here a periodic change of the velocity. And this can be plotted in the Fourier spectra. And we see one main frequency and the harmonic repetition of this. So this is a clearly harmonic signal, a periodic signal. And we look at the same thing in the turbulent state, we get a less periodic, and we get the appearance of different more frequencies. So we are actually here on the transition to a chaotic state. So this is to say, what are the different possibilities to characterize a chaotic transition. Our system of interest, we are working on this system since more than 10 years, is the Belousov Zhabotinsky reaction. It is a chemical reaction system. It is a bromination of an organic species that shows a cyclic periodic color change, which is due to the catalyst, which is ferrin in our case. We have 2 different setups we can look at in this system. We have the beaker setup, which is a bulk solution, where we have a periodic color change of the completely bulk solution. And then we have also the same system, but in a shallow Petri dish, where we can see the formation of chemical waves. It was discovered in the 50s of the last century by Boris Belousov, and later further modeled by Anatol Zhabotinsky. I will not go into all the details of the reaction. If there is a question, I can maybe answer it later. Mainly, we have oscillation between the two states of the catalyst, which is ferrine, which is the blue one, and ferroni, which is the red one. So what is it about the chaos in the Belousov Zhabotinsky reaction? In the very beginning, it was not clear if there is even a chaos possible in the Belousov Zhabotinsky reaction. But in the early 80s, it was discovered that there is also a temporal and a spatial type of chaos. What does that mean exactly? So let's see first the paper by 82. We see if the system is constantly stirred. We see that there is, of course, because of the stirring, no convection and confusion taking place. So we have only a temporal evolution of the color change. So we have only chemical reaction going on. And it was shown that in this system, there is a transition to chaos possible. At the same time, a bit later in 84, it was even shown that in a Petri dish setup, such a transition to chaos can also take place. Here we have no convection because the space is so shallow that there is inhibited the convection. So what would we do actually measure in the Belousov Zhabotinsky reaction? We measure the color change, and this is normally done by photospectrometric measurements, where we send the light beam through the solution and we record the transmission or absorbance of the situation. And this periodic color change is then registered as a periodic change of the signal between the blue down and the red up. And this change of the color is in our system, which is not stirred and open, then after some time going to a chaotic state. Around 2010, we discovered that this state actually is just a transient. So we have here a transient behavior, a chaotic transient, which comes from one periodic and goes to another periodic change. Some researchers call that a type of rebirth. Later then we have discovered that actually this effect was already discovered in the year 1996 by the group around Mauro Rustici and Nadia Marchettini in Italy. What is our configuration here? So for the effect I'm going to describe today, we have chosen a very specific cuvette configuration where we have a very quite slim cuvette with 2 times 4 centimeters and the width of only 0.5 centimeters. We followed the system with the webcam and we extract from the recorded video the green channel, which has around the peak sensitivity, which is important for the ferrine, around 500 nanometers. Now here we can see the time series extracted from the video, which shows the behavior which we actually would have expected. So we have a first periodic phase, which is shown here and magnified down here, where we have around 100 seconds of periodic motion. And then it goes in more or less a chaotic motion of the color change. And here in the meantime, somewhere after 3000, we have also a zoom, where you can see this is a kind of chaotic system evolution. What I have done also is to look at the Fourier spectra of these regions to verify if we are really in a chaotic state. And what we see here is if we look at the first periodic phase, we can clearly see also in the Fourier spectra that here we have a main peak and we have the repetition harmonics of this main frequency, which is around 12.5 seconds. Down here is a bit later in the chaotic phase, and we can see here is not anymore ordered pattern recognizable. And also if we look at the power, it's around 300 times smaller than this peak. So it is more clearly a chaotic behavior. If we look a bit later in this space, which is shown up here and also later here, we can see not a really distinguishable motion, which in fact shows more or less the same properties of more or less chaotic motion. So this is more or less what is already known. We already expected that, but The interesting thing which we have observed in this specific cuvette is that there is the formation of convection rolls. And now I'm going to jump to the video. Let's see if it is working. Okay. So, is the video visible? Also the...
Yes.
Okay, then I will start. So in the beginning, we have a kind of periodic motion. We have the formation of bubbles, which are seen here in green. It's a wrong color image to better make the contrast of, to increase the, and now here we see already the convection cells. I hope you can also see them. This is around 50 times faster than the real time. And we see here the two different convection rolls, which are interchanging and sometimes become the same size. And in the end, we have only one convection roll visible. So there is an interchange between this behavior. And this behavior is, up to our knowledge, the first time that we see a periodic motion in a state which is actually characterized as a chaotic state. Okay. So let's go back to the presentation and see where we exactly see this. So we have 3 times of convection rolls configuration visible. We have the 2 convection roll configuration and the 1. And in between, we have a transition state between a small upper and a bigger down. And if we look at which time point these oscillations are taking place, we see it here. We start with 1 convection roll, which then goes transiting to a second, 2 as a parallel convection rolls, which then again here must be some kind of transition, and we come back. So it's a kind of oscillation between 2 convection rolls and 1 convection roll, but all within a chaotic transient. So if you just look at the color change, you would never imagine that in this state there could be also a periodic motion visible. If you would, for example, we have not done yet this, but if you look, for example, at the velocity field throughout the line in this situation, probably you would observe a periodic motion. At least it's visible to the eye. I hope you have also seen this. So let's come to the conclusion. First, I was talking about chaos if it is a random motion. We have seen that in a very simple system. It is the logistic map that yes and no. It can be deterministic and it can be also random. It all depends on how you look at the system. What we have also seen, it is difficult to identify and characterize chaos. And very importantly, at least for us, it was very interesting to see that chaos is always very important on how you look at the system. You can even have a periodic motion in a so-called chaotic state. So now at the moment, since this is a very new findings, we try to work on a numerical model to simulate the behavior we have observed in our system. At the end, I would like to shortly introduce our group. We are a Living Systems Research. We're a small private research institute, and we're doing research in Austria, in the south of Austria, in Klagenfurt. Thank you for your attention.